Wait, wait.
Ma, èmi pẹ̀lú.
She just started it.
God bless you, honey. God bless you. Come on, see. You never always say, look at see. And say, imagine my we'll manage. Okay. Mm. Mr. Tin works. Morning, all. Please let me know if you can hear me on the chat box. Please, can you tell me you can hear me on the chat box? Can you please off your videos? Off your video. Abomini, Toluwalasi, off your video, please. I don't want to call you. Off your video, please. Okay. Please, can we start the class? Good morning, all, and Happy New Year to all of us. Welcome back to CHM 101, and welcome back to school. I hope you all had a good time. So I will be starting with a recap of what we did last year, so we can join or actually understand where we are. Or for those of us that are joining for the first time, you can at least follow the lecture. Now, remember we are talking about the modern theory of atomic structure, and we started with the summary of scientific method. That's actually the scientists or the earlier thinkers that proposed these structures were the people that actually started what we refer to as scientific method today. Like I told us the last class, that science is not static. Just like you upgrade your phones, your phone software, the bugs get fixed and the new features are added, So also in science, we learn new things. We modify existing things and we make new things. That is new discovery. That is what science is all about. And we all know that chemistry is science. And so in chemistry, we learn new things, we modify existing ones, and we also discover new ones. Now, the summary of a scientific method, like we heard the last year in the last lecture, is that it follows, there's a step to what the scientific method is all about. First, you form your hypothesis. That is a guess. You start guessing, what is this all about? Then you test your guess. Testing your guess is just like forming a model. Then you repeated confirmation of your model is what we refer to as theory. Depending on what your theory is, if your theory fits to what your proposal is, you can now continue to other testing, and at the end of the day, it can even turn to what we refer to as a law. If not, you go back to hypothesis and start okay. So we are recording. So you start all over again. Now, all of this scientific method, like I said, started with the earliest thinkers. Remember, we started with the Democritus, and we say that he actually said that atoms are indivisible. That is, there a point to which you can divide your matter. Remember, everything about atom is also matter. Now, some other person came up, that is Aristotle, and laughed at him and called Democritus a quack. He said that you can actually divide atom to wherever you want, to whichever level you want, and how you want it. That means that you can divide atom forever. Two of these scientists, they are, at that point, they are philosophers. So their argument or their idea is based on philosophical and logical reasoning. But because I told you the last class, Aristotle is more famous, is more influential, his idea was bought over, and this idea was adopted for over 2,000 years. To me, I will actually say it's a kettle calling a pot black, but all the same, two of these scientists, their idea was not, their ideas were not based on experimental evidences. Now, experimental came in times of Dalton. Dalton, like I told you, is a British chemist. But he brought back a Democritus idea that atoms are indivisible. He actually saw atom as the smallest form of all matter. Again, I told you in the last class that Dalton did not carry out new experiments to formulate his atomic theory. What he did was he based his experiments on evidences from laws of what? Laws of chemical combination. These laws were in existence. He just based his argument and experiment on that. Now came J.J. Thomson that discovered the electrons. Now, I want us to have at the back of our mind what the atomic structure is. we know that we have subatomic particles, which are your electrons, your neutrons, and your protons. The proton is in the proton and the neutron are in the nucleus. Now, one person experimentally has discovered electron, which is J.J. Thomson. Now, what we want to look at today is the work of Ernest Rutherford. What was his own discovering, and how did he discover, and how did he make his discovering? Now, Ernest Rutherford was a student of J.J. Thomson. But remember, the last class, I told you that J.J. Thomson experiment was based, or theory was based on what he referred to as plum pudding model. Here, we will understand our pizza. So I used pizza to explain it. It's just the same thing. Just look at the dough that they use to make the pizza. That is the roundish dough. That is what this model look is all about. And now, in the dough, you have your cheese, scattered all over the dough. Now, the plum pudding model is just like that. Thomson sees the atom as the dough being the positive charge of the atom, while you have the cheese scattered all over as the negative electron. But one of his students, which is Rutherford, did not agree with this. Yes, atom contains electrons, yes, which are positively charged or positive ion. That has been described using the gold foil the experiment by Thomson, that is the cathode ray experiment. Now, what he wants to know is he wants to investigate if actually you have the positive electrons, like the negative electrons, just like his father, which is Thomson, has predicted. He sees it that, for this to exist, there must be something holding that particular electrons, because like charges we know will repel each other. If you have an electron scattered in the dough, which is positively charged, we wanted to be sure that you have that charges in the atom of both positive and the negative. And how did he carry out this experiment? He used what we call the gold foil, and that is why Ernest Rutherford experiment is referred to as the gold foil experiment. Now, just for us to, have a bit relaxation, to laugh, I was now wondering, to me, gold to us is an expensive thing. I don't know what gold foil meant, if it is much more cheaper than aluminum foil or tin foil, because all of this will also generate positive charge with the experiment that he did. But that's by the way. Let us explain what Ernest Rutherford actually did. He took the gold foil. We are going to go to, like I said in this class, it's going to be like story. Now, he took the gold foil, and like his mentor did, he also shot an alpha particle on it. The alpha particle was generated from this source, lead container that has a radium. That is where the stream of alpha particle were generated. Now, when he shot this alpha particle on the gold foil, the alpha particle, as we know, are positively charged. So what he thought was that, okay, since you have negative charges here, and you have you have positive charge on the dough, and you have negative charges as the electron scattered. His assumption was that once this stream of alpha particle hits this gold foil, that everything will go straight onto the photographic film or the luminescent screen. But to his dismay, what he found out was not that. He found out that all the alpha particles did not go straight as was predicted by J.J. Thomson, but some of these particles bounced back and some deflected to the sides. So if some bounced back and some deflected by the side, now Rutherford now thought that there is something happening that is not just that you have the positive charge, being embedded in the dough and the negative electrons scattered all over it. If that is the case, he assumed that there are two possible things that could be happening. Now, one is that whatever that is making this ray, these alpha particles, to bounce back, must be that maybe this alpha particle has hit something hard in the middle of this foil, because the alpha particle were shot through the middle of the gold foil. If it is bouncing back, probably it has met something strong that made it to hit back. It's just like when you hit your head on a strong wall, you will fall back as if, or when you hit a ball, on a strong wall, it will fall back to you. That is his assumption. Another thing again that could be possible is this. Maybe there is something there that is also a positive charge. That is something in the middle of that gold foil where the alpha particles were shot, because alpha particles were positively charged particles. And so we know that like charges will repel each other. And so if there is something that is deflecting by the side, that means that thing there is a repulsion. Whatever that is there is having a positive what? A positive charge to repel the positive charge from the alpha particle that is being shot in the middle. Now, that is what the assumption that J.J. Thomson made. And so when that happened, he now used other sources to release the alpha particles and shot in the middle of the gold foil. And like I said, at every point in time, he got the same result. Now, his conclusion was this. His conclusion was that in the middle of this foil, because he's representing the foil, the gold foil, as an atom, in the middle of this foil, there is something hard, which is referred to as hard, dense nucleus in the middle. And again, he's now said that because some of the alpha particles deflected by the side, whatever that is here has a charge which is the same with that of the alpha particle, and that is a positive charge. And so he now concluded that there is a positive charge concentrated right in the middle of that right in the middle of this foil, where you have a hard, dense nucleus. And so he now said, okay, and for this particular atom to be stable, there must be what? There must be electrons revolving round it. Because we know that if there is no attraction, repulsion will always cause instability, and the atom will collapse. But we have never heard that an atom has ever collapsed. And so he now resolved that in here, you have a hard, dense something, which is referred to as the nucleus in the middle, and there is a positive charge that is concentrated in that middle. And this is what he referred to as what? The proton. So now we have the proton and we have the electron. So just like J.J. Thomson discovered the electrons, one of his students, Rutherford, also discovered the proton. Now, all this you're going to see in this slide, it is what I have explained. Like I told you, I'm going to tell you a story that you will always remember, and not making you to cram any kind of thing. Then we go to the third particle, the third subparticle, which is your neutron. This third particle was also discovered by a scientist named James Chadwick. James Chadwick also is a student of Rutherford. So see the way that it goes. Like we said, science is not static. There is modification. Your mentor found this. You're not debunking what your mentor found. You're just modifying, improving what he or she has discovered, to make a meaning out of it. Now, the neutron was the last of the subatomic particles to be discovered. Now, there were a few clues that led John Chadwick to think that there must be something in the nucleus that helps keep the proton from repelling each other. Remember, the electrons are not in the nucleus. The electrons are revolving around the nucleus. You only have your proton in the nucleus. And if you have proton in the nucleus, assuming you have 3 protons, maybe you have an electron that has 3 protons in the nucleus, and you only have these protons, they will repel each other. And like I said, there will be a collapse to the stability of the atom. So James Chadwick now, he started thinking, for this nucleus, for something to hold this together, there must be something that is keeping it from not repelling each other. Another clue that came to him was this. Now, scientists at that time know about atomic mass units. And we know that helium has 2 protons, but the atomic mass unit of helium is 4. So what James Chadwick did is this. He now said, okay, if that is the case, if I bring 2 hydrogen atoms, one hydrogen atom is made up of 1 proton. Another hydrogen atom is made up of 1 proton. So if I bring 2 hydrogen atoms, I will be having 2 protons, which means that the weight of 2 hydrogen atoms, if there is nothing else in the nucleus, that is only proton that is in the nucleus, which means that the weight of 2 hydrogen atoms must be equal to the weight of 1 helium atom. So when he looked at this, he found out that no, that the weight of 2 proton atoms is not equal to the weight of 1 helium atom, but the weight of 4 hydrogen atoms is equal to the weight of 1 helium atom. He now concluded, of a truth, there is something else in the nucleus other than proton. And so, how did he conclude this? He now concluded this by, carrying out an experiment. This experiment that he did, he actually took beryllium and now shot an alpha particle just at the same way that Rutherford did, or Rutherford shot an alpha particle on a gold foil. But this one, James Chadwick shot an alpha particle on beryllium atoms. Now, this alpha particle were also generated from a source. It was generated from a polonium source. Now, he shot an alpha particle on the beryllium atoms and discovered that rays were being released from the atom. The rays that were being released from the atom, he was not sure of what is coming out, but he was sure that whatever that is kicked out from this atom, it does not have charge. And so to prove this, he now puts a paraffin. A paraffin is a wax, just like candle or wax. A paraffin in front of the rays. Why what he did was, he just wanted to know what is coming out of this ray. So when he placed the paraffin in front of the ray that is coming out, so the ray that is coming out are actually going through the paraffin. And when they went through the paraffin, he discovers that protons were shot out of the paraffin. And protons, like we know, are positively charged. But he was sure that whatever that is coming out is chargeless. But whatever that is coming out does not have a charge, but it has the same size and the same mass with proton, for proton to be coming out. And so, who is this, please? Who is this? Do you want to continue with the class? Now, you now concluded that whatever that is coming out from that beryllium atom, when you hit it with alpha particle, must be about the same size or mass with the proton that is shot out. But he knew that it has no charge. And this was how neutron was discovered. And so, in the nucleus, you have your proton and your neutron, while the electron revolves around the nucleus. And so, with the discovering of the neutron, we now have an adequate model of the atom. And so you have your atomic structure being made up of the subparticles, which are your electrons, your protons, and your neutron. Now, before I go further, I want to let us know that at this point in time, all that we've been talking since the beginning of the modern theory of atom has been particle, particle, electron as a particle, electron as a particle, electron as a particle. Now, the model of the theory of Dalton, the model of J.J. Thomson, the model of Rutherford, and that of James Chadwick, they are all referred to as classical models. They are referred to as classical models because they view electrons as only having a particle, as only being a particle in nature. The nature of electron is just as a particle. They are not seeing any other nature of electron, either as being a wave like a quantum model. They are just viewing it as being a particle. And so they are referred to as classical models. Now, from now on, I'll be looking at Niels Bohr, the proposal of Niels Bohr and all of that. From Niels Bohr to the other scientists that had an input in the discovering of atomic structure. Their models were referred to as quantum mechanical models. Quantum mechanical models because they are looking at electron as having both the particle nature or particle property and the wave property. So they are looking at the duality of what? Of electrons. The duality of electrons in terms of their particle nature and in terms of their wave nature. So you see particle wave nature of electron. That is what it's all about. So we have two major models when we are looking at the atomic structure or the history of the atomic structure. We have the classical models and we have the quantum mechanical models. Like I said, all that we've been saying up till James Chadwick, they are referred to as classical models. Now we want to look at the quantum mechanical models. Now again, let's continue with our story. Even as I show this slide, I will still give it to you as a story. Who is this disturbing my class? Please, can you mute yourself? Now, Rutherford atomic model was quite commendable in explaining the structure of atoms because we now know that in the middle, in the center of the atom, that the positive charges are not scattered the way J.J. Thomson looked at it, but they are in form of a dense, they are hard dense in the middle. So they are just a small spot in the middle of the structure of atom with a positive charge, which is referred to as proton. Now, however, this particular proposal or theory by Rutherford was not very appropriate theoretically. Let me tell you why it is not appropriate theoretically. We know that if you have any charged object, like electron is a charged object. You know that Rutherford told us that you have the electron revolving around. Like I was saying, any charged object like electron that is revolving around a circular motion, it will gain acceleration. It will gain momentum gradually. Even you as a human being, just be turning circle. At a time will come when you feel dizzy and you want to fall. True or false? Let me hear you on the chat. I mean, go to the chat box. True or false? You'll be turning round. There comes a time when you will begin to fall. You will lose control. You will start feeling dizzy. You will start feeling weak and all of that. True or false? Good. So also is any charged object. Now, for Rutherford to say that the electrons are revolving around the circular motion, it means that at a point that this electron will begin to gain acceleration. And when they begin to gain acceleration, they will liberate energy in any form. And if they continue to give out this energy, a time will come when all the energy in the electron will be over. They will be given out, and the electron will fall into the nucleus. What this means is that atoms are unstable, but we all know that atoms are stable. So it is true that Rutherford atomic model was quite commendable, but it was not very appropriate theoretically, because you cannot use it to explain the stability of what? Of atom. Now, what happens is this. Because the nature of how atoms are stable, meaning that Rutherford circular movement of electron is incorrect. But although it is not really incorrect, but there is the hypothesis. It is a hypothesis. This hypothesis needs some modification. And this is what is being put off here. Remember, we started with science is not static. You get new things, you modify existing ones, and you discover new ones. Now, Niels Bohr is Rutherford student again. This is very interesting if you're following the story. Niels Bohr is Rutherford student. So he now modified this hypothesis by adding additional explanation to describe the atomic structure, just to make sure that there is no circular movement the way Rutherford said it of electron, to prove that atoms are stable. So he said that instead of electrons, saying that electrons, they move in a circular way, that they travel around the nucleus like a planet travel around the sun. We know that the planet has never, ever gotten into the sun. It continued to revolve in the sun in a fixed path. So you never find any planet jumping to a different path all of a sudden, no. So in that same way, as they move circling the sun in a fixed path, so also we have the atomic structure. The nucleus is in the center, acting as the sun, located in the center, and the electrons, like the planets, revolving in a fixed definite orbit, which is referred to as energy levels or shell. So Niels Bohr postulated that electrons, they revolve around the orbital, and in that way, they do not radiate energy because they revolve in a fixed path. And this justifies what we now refer to as energy level. Each shell has a defined energy level. So Niels Bohr modified Rutherford what? Rutherford theory or proposal. Now, in summary of Bohr's atomic theory, what he actually meant is that an atom will have certain allowable quantized energy states. Now, you have the energy level 1. But before now, let me go to something. Okay, let us look at what we have here. You have the n equal to 1, that is energy level equal to 1. So electrons that are in n equal to 1 will be in n equal to 1, except if they absorb energy or they emit energy. That is when they will leave this particular fixed path. So something external has happened to that particular electron. Now, n equal to 2. So electrons move around the nucleus in a loud circular orbit. So there is nothing like, you have it revolving in a circular motion, just as Rutherford proposed. You have them in a loud circular orbit. And each level has a maximum number of electrons it can contain. So that also controls it. That is what Rutherford actually made us to know. Now, another scientist, which is we refer to as Erwin Schrödinger, also further explained or improved on Bohr's findings. He did not do anything different. He only used mathematical equations to describe the possibility of finding an electron in a certain position. Okay, it's true that you have energy level where you can find electrons. Where are these electrons actually located? Where can you find them? That is what Schrödinger is all about. The probability of finding an electron. And the probability of finding this electron is greatest where the cloud is most dense. And so where you have less dense cloud, there is less likely electrons to be there. And so this model is what actually introduced the sub-energy levels. Like you have in the second energy level, you have your S and your P, S and P and all of that, F, P, D and all of that, your orbitals. So he is telling us that, yes, electron is in this shell, but this electron now, for example, I have 6 electrons, and I want you to tell me where I will find the 5th electron. If I write the electronic configuration, you will know that it's going to be 1s2, 2s2, and 2p1. So the 5th electron, 2p2. So the 5th electron is going to be in the p orbital. It could be in any of the orbital because p orbital is degenerate. Unlike Paul just said that you will find it in second energy level. Yes, you find it in second energy level, but where in particular will you find it? So that is what Schrödinger model is all about. So he actually improved on Bohr's findings by letting us know the likelihood or the probability or where you can find an electron in a certain position. Now, I have this diagram here to explain it much better. Like I said, this is this is where you have your what? Your proton. Because you have 2 electrons in this shell, 1 electron in this shell. All the electrons you have in this particular atom is 3 electrons. And so you have 3 protons. Here in this position, they are still quantized. Electrons, you cannot find the electrons here. You can only find the protons. But you can find the electron in this shell, or you can find this electron in this shell. So depending on what happened, the electrons can be excited to any of the shell, even in another shell, depending on the energy it's acquired. If it acquires energy that will make it to go from n equal to 1 to n equal to 4, it will go there. So that is where you can find your electrons. Now, this is the summary of Bohr and Schrödinger model. Now, you have other scientists that have also contributed to the concepts that shaped modern electronic theory. But before we go into that, I want to, okay, I want to quickly, I don't know if, I want to quickly give us just, a class work. It's very simple, but we need to do something. Now, I want you to calculate the number of electrons. The number of electrons that n equal to 4 can hold. The number of electrons that n equal to 4 can hold. Me, I have to do it here because it just came up now. Remember, there is a formula. I think we should go back to the formula. Each energy level can hold the number of 2n squared number of electrons. So if you have n equal to 4, how many number of electrons can it hold? So you do that, then we'll go back to the I know it's 2n squared, but I want you to tell me the number of electrons. Correct. Correct. Everyone who has written it is correct. Correct. I just want to bring some questions. I think I should be able to get some more questions for the class. Since we have still have some time to. Okay, just give me see, this thing is usually giving me trouble. It's okay. I'm going to get back to you now. Please do not leave the class. I'll join you shortly. I want to get more questions so we can. All right, good. Now I have this question. It says, what was thought about the inside of an atom according to Thomson's model? What was thought about the inside of an atom according to Thomson's model? We are talking about Thomson, not Rutherford. It was mostly empty space. A. B. It was a plumb of negative material with positive charges embedded. It was a plumb of positive material with negative electrons embedded. Which is the answer? A, B, or C? A says it was mostly empty space. It was a plumb of negative material with positive charges embedded. It was a plumb of positive material. C says it was a plumb of positive material with negative electrons embedded. Which is the answer? Okay, sorry, chat. Nobody has answered me. Okay, okay, okay. Okay, we are going to go back to the question. It's good I'm asking these questions. I'm so happy I'm asking them. Okay, let's go back to the question now. Let's go back to the question now. It says, what was thought about the inside of an atom according to Thomson's model? Remember, I told you that you should look at the inside of the atom as your pizza. You know your pizza, you have your dough. the round dough and the flour that they use in making the pizza. He assumed that the dough has a positive charge. Then the cheese that you have embedded there are the electrons that are negative. So that is how Thomson viewed the inside of an atom. He called it the Plum-Pudding model. But Plum-Pudding is actually this thing, what do they call it? It's American. It's not even the British will not understand it that way. Then I now used our own pizza that you will understand, because that is just a good concept for you to understand it. You have your dough, the second one, filled up with positive charge, which is positive material. Then you now have the cheese embedded in it, and the cheese are the electrons. So can you go back to the chart and give me the answer? Those of you that gave me a wrong answer. Was it a plumb of, was it an mostly empty space? Was it a plumb of negative material with positive charges embedded? Or was it a plumb of positive material with negative electrons embedded? Which one? I'm taking the start all over. Even if you have answered, you can't see. You're not seeing what I'm saying. I'm making up questions myself. I didn't put them on that slide. So just join the class. Those of you that got the wrong answer, can you now, I know your name, I don't want to call your names. Can you now correct yourself? I want to see you correct yourself before we go move forward. Okay, so let's go. The answer is C. The answer is C. It was a plumb of positive material, which is your dough covered with positive charge, with the cheese, which forms your electron embedded. So the cheese are embedded in it. So the answer is C. It was a plumb of positive material with negative electrons embedded. So let's go to the next question. The next question says, okay, this one, everyone should get it right. What was the name of the J.J. Thomson's accepted model of the atom? Is it solid sphere? Is it Plum-Pudding? Is it nuclear? Is it electron cloud? A is solid sphere, B is Plum-Pudding, C is nuclear, D is electron cloud. What is the name that J.J. Thomson gave his model? Is it solid sphere? Is it Plum-Pudding? Is it nuclear? Is it electron cloud? Give me the answer. Let's move on quickly. We have just a few minutes. Which one? Okay, good. Yes, good, correct. If you don't know the alphabet, you can just write the name of the model. No, now we saying solid sphere now. When you people write something like this, I get worried. Because I want everyone to just follow the story. Okay, correct. That's Plum-Pudding. Now you're going to tell me who discovered the proton? Who discovered the proton? Who discovered the proton? Can I have the answer quickly? Who discovered the proton? Who discovered the proton? And good, correct. Not energy. I think it's It's a typo error. Who is telling me J.J. Thompson now? Can you please correct yourself? I don't want to call your name, but correct yourself because I want to see you get the right thing. Then before I will go. Now, those of you who got the answer, can you also tell me who discovered the neutron? Who discovered the neutron? So we know who discovered the electron, the proton now. Can you tell me who discovered the neutron? Good, correct. Now you know your exam is going to be a multiple choice question. So these are the things you look out for. It's a multiple choice question, please. You look for the most correct question. Answer, sorry. Good. So let's go to complete our story so we can end. I can end the class with you. Let's go back. Can you see my slide?
Let me mute myself.
Okay. Sorry. So I need to.
Mommy said that we should not touch that soup.
Who is this again? I want to minimize this so we can continue. Not this. Don't mind that guy Toluwala Siabiweti. He has been disturbing my class since. No. J.J. Thompson did not call it proton. He was just using the positive material to explain the plum pudding model. What he discovered was the electron. He sees the electron as scattered. Remember, like we said, that you must have something to hold together. The atom must be stable. So he knows that for the atom to be stable, there must be something positive to hold the negative electron. So he did not discover the proton. He did not discover the proton because the protons are in the nucleus. So it is Rutherford that discovered the nucleus, that actually discovered that there's something positive in the nucleus, and that thing positive in the nucleus, he called it proton. So don't confuse yourself. Remember that, like I said, it's not as if they are making up the structure by themselves. No. It's just like going from known to unknown. Yes, the substructures are there. It's just to explain what has happened. Do you understand? Atoms are stable. Atoms are existing. So he did not discover protons, please. He discovered electrons. Rutherford, who is a student, discovered the nucleus. And because the only charged particle in the nucleus is the proton, he called it that means he discovered that there's a positive charge in the hard, dense nucleus. He discovered there's something in the middle of the atom that is hard. One, and that hard thing it has a charge, a positive charge in it, which he referred to as the proton. Then James Chadwick now said, okay, for us to have proton and it's not falling off, there's something there that will do what? That will complement it, that will hold it, which should be a negative, which should be something different. So for that to hold, he has some clues that I told you, and he discovered that, okay, you have neutron here. So your neutron and your proton is what makes up your nucleus. Because if you say that you only have your proton, that means that if you're looking at the atomic mass of 2 protons, it's going to be the atomic mass of any atom that has 2 protons, which I explained that it was not true. Good. Yes. James Chadwick discovered the neutron. Yes, you are correct. Discovered the neutron. Now let's look at other scientists that collectively contributed to the concept that shaped the electronic theory. These ones that we are looking at now, all of them, they are discovering, or their model, they are all under the quantum mechanical models. So we start with the Rydberg. The Rydberg discovered that there was an integer relationship between the wave numbers of successive lines. He actually discovered the spectral lines. So he described the wavelength of lines in many chemical elements. And so what this means is that he's saying that for you to go from N, that is energy level 1, to energy level 2, that you must have what it needs, or the energy that is required to move from one energy level to the other. So he gave a relationship between the wavelengths and the energy levels, or energy transitions. He used the hydrogen atoms, but that we can extend to other atoms. Now, Max Planck actually looked at quantization in helping to explain why atoms emit light at specific frequencies. So it contributed to understanding what we refer to as electronic transition within atoms. So that is what Max Planck is. All of this is just an additional to what the modern atomic theory it's all about. And that is why I brought them in summary at slide 84, that you just look at each of them and know what each of them it's all about. Now you have the photon theory, which is also described by what? By Albert Einstein. He also introduced the wave and the particle nature of what? Of that light, because you have the spectral lines, which are light. He expanded this idea to saying that light, you can also think about light the way you think about electron, as having both a wave and a particle nature. And he gave an equation which is referred to as the equation, the photo, he introduced the photoelectric effect, and he gave the equation which he referred to as energy is equal to the mass times the speed of light squared. I will share the slide. People are making me to be confused. I will share the slide, don't worry. I will share the slide. Let's finish the class first before you start talking about sharing slide. So now you have again the Browning. The Browning looks at the wave and particle duality of light again, and he brought an equation, of a moving particle, and he gave that as he described that using this equation, that the wavelength is equal to the Planck constant divided by the the Planck constant divided by the momentum. And we know that momentum is also given as mass times velocity. So you can actually substitute that with mass times velocity. So what this is all about is that you can apply the wave-particle duality concept to all particles. It's not only to light, as Albert Einstein said. You can also, apply it to all other particles. Now, the Heisenberg uncertainty principle is the one that is telling us that you cannot know the position of a particle and the momentum at the same time, that you can actually know one at a time while you keep the other constant. So we know the position or the momentum accurately, but knowing the position and the momentum, it's not possible. So, but you know that in classical model, it's assumed that you can measure both, that both can be precise. But in a quantum mechanical model, the position and the momentum of a particle cannot be measured simultaneously. What this means is that I always tell students, just look at when you have a mosquito in your house. If you have a mosquito in the house, if you switch on your lights, you will see the mosquito. That is the what? That is the position of the mosquito. Now, but once you switch on the light, what happens? The mosquito will just fly. It will fly away by speed. So you won't even be able to determine the momentum. But if you want to determine the momentum, what you need to do is, you might not know the accurate position. All you need to do is to dim the light in the dark. Just don't make the light to shine too much. You can now use where the mosquito is. Maybe is where he's doing that is sound, to locate where he is. Even without much having enough light, you can actually track where it is, and so on. So that is what this is all about. You can accurately know the position. The more you know the position, the less accurately you know the momentum. And the more you know the momentum, the less accurately you know the position. You cannot know both accurately. Now, in summary, I said here that the quantum mechanical model has replaced the classical atomic model, which that is the earlier model, due to its ability to predict and explain atomic phenomena, including the chemical bonding and the spectral lines. That is, they can explain both the wave and the particle property, or the particle nature of the atom. Like I said, the classical models describe the electron as a particle, whereas the quantum model explains the wave and the particle duality of an electron. That is what makes the quantum mechanical model significant. Now, the classical models include that of Dalton atomic model, the Thomson-Plum-Pudding model, the Rutherford model, James Chadwick model, while quantum mechanical models consist of from Bohr, Schrödinger, and the contributions from other scientists. So, like I said in summary, there are some textbooks that instead of modern electronic theory of atom, you will see quantum mechanical model. They are all the same thing. Some textbook change the name from modern electronic theory of the atom to quantum mechanical model. All of them reflect the significant advancement in understanding what has happened in the atomic structure through classical model to quantum mechanics. And so with this, I want to appreciate all of you and to say a very big thank you for attending the class, and more importantly, for participating, because I can tell you, I really enjoyed your class. You all were participating. Everybody wants to answer the question. Everyone wants to ask question. Who is sending attendance? Don't send me attendance. So that will be all for now. Please if you have any question regarding how you get linked to the Telegram channel, okay, please, can you ask your class reps? There should be a link to the class. I don't know, but you should just ask your class reps. They should be able to tell you how you get the link to join the Telegram. Now, once I'm done with this class, I'm going to yes, I'm going to upload the, what do you call it? The last part of the class. I've uploaded the first part. I'm going to upload the last class, which is the class we had today, and then that will be all for now. So please, if you have any question, you can see me in my office. My office is Foundation Building, room 230. My name is there, Dr. Dueke-Eze. My name is on my door. You can see me there. Someone asked a question about planetary model. That is born now. That is born. I told you the story now. So any other question? Any other question? I told you people that it was Bohr that says that he looks at the electrons, the way they travel around the nucleus, like the way the planet travels around the sun. That is the planetary model. That is Niels Bohr. It's not who is saying the Brawling field. Yes, all of these are theories. They are not law. Even these days, some laws are being pulled down. Some laws are being debunked. You could hear that some laws in chemistry have been put down. So that is it. So can we call it a day? Bye for now, and please read in between and be sure you will come out well. Thank you so much. I said foundation building. Let me be sure of the room. I think it's room 230. Wait first. Yeah. Foundation building is behind the chemistry lab building. The building behind the chemistry lab building, that is the foundation building. Room 230, 230. My name is on my door. But most importantly, I am, if you want to see me, please, Thursdays is better. Mondays, Thursdays, yeah. Because I have lab on Friday, and on Tuesday I have some other assignments. So you can always see me on a Monday or on a Thursday. Thank you so much. I enjoyed your class too. You guys are good. You were participating. Everyone wants to answer. Everyone wants to understand. And so I wish you good luck in your exam.
Amen. Thank you, ma.
You're welcome.
Thank you, ma.
Welcome.
Thank you, ma.
Welcome.
Thank you very much, ma. Really appreciate it.
Thank you.
Thank you, Ma.
Thank
We
you, ma.
enjoyed your class.
We enjoyed your
You
class.
guys are welcome.
Thank you, ma.
Welcome.
Thank you, ma.
Thank you, ma. Go and have
Thank
your
you.
breakfast. Or you go and eat. Breakfast is very important.
Ma, you to go and eat too. Breakfast also very important.
I will go and eat, but I was not the one that yawned that way now. That yawning was too much.
Thank you, Ma. Your class was great.
Thank you, too.
Thank you, ma. Thank you very much.
You're welcome. Thank you, too, for not disturbing my class. You guys behaved yourselves. And thank you for active participation from all of you. So we can go